Okay, let's get it started. It's my great pleasure to introduce you Dr. Kazuyuki Miyazaki. So Kazu got PhD in 2006 at Tohoku University in Japan, and then working for Jamstack for 12 years.
Yes.
And then moved to this country, JPL 2019, that's a year before the pandemic.
Yeah.
And then he has been working on the satellite process. And then I met him, I think when he was at Jamstack during the course AQ, yes. And he contributed quite a bit our understanding on the air quality and atmospheric composition using satellite. So, floor is yours. Thank you very much.
Yeah, thank you for that introduction. And I need to turn on this microphone. I hope people can hear this. Okay. So thank you for this really great opportunity. I'm really glad to be invited by UCI. This is my second time to visit this campus. The first time was I think a few years ago, Chorus AQ, the conference that the people here organized. And I was really impressed by this beautiful campus and the people here. And I'm, Kazu Miyazaki. I'm a research scientist at NASA JPL. And I'm also working at the UCLA as a visiting project scientist or something. So I worked together with many students at the Caltech and also UCLA. And we'd like to have some new collaboration opportunities with UCI in the future, especially if the people here are interested in using the satellite data from the NASA's missions. That would be, I think, great framework to work together toward the part of the atmospheric composition research project. So the idea would be very welcome. Okay, so today's the presentation title is the atmospheric composition modeling, data assimilation, emission estimate using the multi-constituent satellite observations. Okay, so that's probably many of you already know the air pollution is one of the most important major contributors for the human health. So it can reduce about 20 months of the human life in average, but with the substantial spatial patterns. Then as you see here, the current in situ observing network is clearly insufficient for the global health impact assessment, especially in the developing countries. I mean, the current observing network covers only the United States and some part of Europe, and also the East Asia, mainly South Korea and Japan. Then the long term, regular surface ozone monitoring network covers only roughly the 17% of the global population. So that cannot tell us what the impact of the air pollution on the human health, the exposure. And at the same time, the satellite measurement have provided the unparalleled sources of the global data, but still suffer from the limited surface sensitivity for many key species. They can provide some sort of the current information for the entire atmosphere or troposphere, but having the near surface sensitivity has been challenging for many years. So then the limitations of the different observing network system can be mitigated by the new state-of-the-art chemical data assimilation systems that optimize the information available in those data sets. And that's my main research topic at NASA JPL. So this figure shows the many previous and the near future satellite missions, for the Earth, this planet that we are working on. So the availability of the satellite, the derived measurement of the various chemical species has been enhanced in the past, especially the 2 decades since 2002, for studies of the long-term variation within the atmospheric environment and the climate system. But information obtained from the individual satellite is limited, and the combined use of those multiple satellite data is challenging. That is related to the differing vertical sensitivity profiles and different overpass time and mismatches in the spatial and temporal coverages between the satellite instrument. as well as the missing information on the chemical regime or some meteorological conditions. Just a moment. Then we use the data assimilation technique to combine the different multiple satellite observation. So data assimilation is a technique to extract the signals from noisy observation by acting as filtering, and it interpolates the information in space and time. That is interpolation. And also reconstruct the state variables that are not sampled by observation. That is called the completion. Then for the atmospheric composition data assimilation, we use the data assimilation technique to make best use of all available data from heterogeneous sensors scattering in space and time, and to produce the chemically and dynamically consistent integrated data set. And also to extend analysis on non-observed space and species. As shown by the bottom right figure, we can fill the gaps between the individual measurement by using the data assimilation techniques by propagating the observational information through the modeling, the calculation. So there are many important applications of chemical data assimilation, such as the air quality and the UV monitoring and forecasting, and the emission source inversion, radiative transfer calculation, and the chemical reanalysis. So similar to the meteorological reanalysis data that have been used in many climate studies. So it's the basic, the chemical, long-term, the chemical data assimilation output can be used as the reference, the long-term data of the atmospheric composition. So here I'd like to introduce the chemical data assimilation system called MOMOCHEM. So this system combines the multi-constituent observational information from the multiple satellite sensors. Then one of the unique points of this system is the use of the multiple forecast model. So we can provide the uncertainty information in the data assimilation output due to errors in the model processes in this way. Then our reanalysis output have been validated against many independent observations that include the several NASA's aircraft campaign data, including the CORUS AQ and some others that were conducted over the North America. Then this data provides so far, not 16, but the 17 years record of the atmospheric composition. That's the 3D 2-hourly global surface to the lower stratosphere. Then it includes the chemical concentration of 35 species, as well as the emission sources of the ozone and aerosol precursors. So this system provides the anthropogenic, biogenic, and biomass burning and lightning emission sources of those NOx, CO, and SO2. Then this data has been used in many or some science application, including the validation of NASA satellite product. So that this data can be used as a reference data to check the quality of new satellite product. Then this system can also support the observing system simulation activities in support of mission formulation. I mean, before having the actual measurement, we can measure the potential impact of that new satellite measurement using some ideal measurement in data simulation. So then the people might know the ECMW CAMS product. I mean, that's the chemical reanalysis product. And it has been very widely used in many applications. The major difference between my reanalysis and the CAMS is the inclusion of the emission optimization in our system. But they do not have that component yet, but they have even more the satellite constraints to represent the atmospheric composition 3D structures. Okay, so this slide shows how the data assimilation constraint the tropospheric chemistry system for the decadal Aura satellite era. So Aura is the name of the satellite, which was launched in 2004. Then our data assimilation approach simultaneously optimizes the concentration and emission of many species, including the emission sources. Then the individual assimilated data provide information on the different aspects of the tropospheric chemistry system. Then the assimilation of the many chemical species can be expected to improve the emission estimate. For example, the assimilation of ozone or some others, we can affect the lifetime of the NOx in the atmosphere. Then that improves the lifetime representation in the model, can help to have the better estimation of NOx when assimilating the NO2 measurement. So this can be different from the traditional, the single species, the inversion system to infer emissions. Then using that system, we have conducted the decadal tropospheric chemistry reanalysis calculation for 2005 to 2021 so far. So this data can be used to understand processes controlling the atmospheric environment and to provide initial and boundary conditions for the chemical and climate simulations, and also to evaluate climate models and also the bottom-up emission inventories. And some statistical information such as the increment due to data assimilation can be used to suggest the development of the future the observation, or can tell us the weakness of the current model by looking at the adjustment from the model prediction to the data assimilation analysis. That information can be very useful to make further improvement in those systems. Okay, then more recently, we utilized the multi-sensor data, new multi-sensor data from the SOMI NPP, including the CRIST, BEERS, and also the AIR's OMI, that's the multispectral retrieval developed by the JPL project. In addition to the recent TROPOMI measurement to characterize processes that form ozone and aerosol, and that determine the interaction between the trace gases and aerosol. So this new satellite error chemical reanalysis framework can provide the more detailed information on the changes in the secondary pollutant. Then, and their attribution too. So using this updated framework, we are currently working on the development of the TCR3 version 3 data. Then the air quality, the analysis system can also benefit the greenhouse gas studies. For example, by having some improved representation of OH for the globe can help the CH4, the simulation and the inversion, and the analysis of the core emission sources, between the air quality and GHGs, such as the NOx and CO2, the core emission sources analysis can help to make the better estimate of the fossil fuel CO2 fluxes. So those will be discussed briefly later in this presentation. Okay, so then as an international activity, Dylan Jones from the University of Toronto and Helen Warden from NCAR, and I are leading the IGEC, the TOR2 Chemical Reanalysis Focus Working Group. So TOR2 is the Tropospheric Ozone Assessment Report, the project, having the global linkage measurement to study the long-term or short-term changes in the ozone. We are coordinating the couple of the working group. Then this chemical reanalysis working group is the one of them. Then the main objective is to evaluate the current capability of the chemical reanalysis, validated against the TOR2 observation to assess their potential for the ozone analysis studies. And we are also working on the assessment of the relative importance of the individual observation to improve surface ozone analysis. In this case, we used so-called observing system experiment. By assimilating the individual measurements separately, we can measure the relative importance of the individual measurement to better represent the ozone spatial and temporal patterns. So this would help to design the observing system that better capture the ozone variations. Then some of the reanalysis provide the top-down precursor emissions. So those intercomparison and analysis of ozone using those data could help to understand the ozone in the precursor trend analysis. Then another activity we have is the assessment of the representativeness of the individual in situ measurement, for example, from the ozone zone measurement, FTIR, and some other aircraft data. So the complete 3D field from the chemical analysis can be used as a reference, the ozone map, to evaluate the individual measurements, the limitation to represent the regional or maybe the continental scale ozone mean states and its trend. So we are working with the observation community to clarify the limitation and the advances of the observing network, not only the surface ozone. Okay, so this developed the data assimilation framework. The emission optimization provides important information on global air pollutants and its impact on the human health and the climate. So here, the right figure shows the decadal changes in the spatial distribution of ozone since 2005. So which shows the substantial global shift in the anthropogenic emissions, in this case for NOx. For example, from 2005 to 2010, there were shifts from the Europe, the Japan, and the United States to China. Then afterwards, they're from China to India and some of the Middle Eastern countries. Then in more recent years, we see the increase over the southern China and the India and some southern Asian countries. Then the left figure shows the temporal changes in the NOx emissions over the 2 decades. So China showed the strong increase in NOx emission till 2011 and started to decrease after 2012. Then since 2016, there is a slight increase again. Then the India shows the continued increase over those 2 decades. Then the Europe and the United States shows substantial reduction, but with some slower reduction in the recent years. So while they're showing the substantial changes for many regions of the world, the global total NOx emission kept almost constant over this period. So it's like more like the shift of the emission location while keeping the total in the same level. Okay, so assessing the effectiveness of the surface air quality regulation is complicated very much by non-local sources and the sparse in situ observation network. So using that estimated emission from our data assimilation framework, so we identify the Asian contribution to the background ozone over the United States. So the right figure showed the ozone anomaly due to Chinese NOx emission changes since 2006 in the left panel and since 2011 in the right panel. So that increase in Chinese NOx emission from 2006 to 2011 had substantial impact on ozone across the northern exotropics, which increased the daily average ozone over the southern California by up to 4 ppb in the lower atmosphere. Then the reduction of the Chinese emissions since 2012 to 2016 led the similar magnitude of the ozone reduction in over those similar region. Then we also assimilated satellite-based tropospheric ozone profile measurement over Asia in this exercise to see its impact on the analysis of the US background ozone. And we found that it substantially modified the global ozone, including the US surface ozone concentration. So the measurement of both ozone and its precursors over Asia, for instance, by James, constrained by James measurement, can play a substantial role in evaluating not only the local, but also the US and the global air quality. So the global, information propagation, the content is really key to have the better representation of the changes in the background, the concentration of ozone and many other species. So this slide shows the decadal ozone changes. Between some satellite measurement and model simulations without any data simulation, and the chemical reanalysis calculation that did not use any direct tropospheric ozone measurement. Then the upper figure compares the 2005 to 2010 time series of the mid-tropospheric ozone over China with the tropospheric ozone satellite measurement. So the assimilation greatly improves the model's representation of ozone. Is microphone working? I think it's gone, right? Yeah. It's on still.
It's on.
Yeah, maybe battery is.
Battery. Oh, it's off.
It's on.
The microphone works.
Works. Okay, I think this is. You are using your.
I don't need this one anymore. Right?
You don't need that.
Okay. Yeah.
I'll try to figure it out.
Thank you. This is better. Yeah. Okay, then the people on Zoom can hear my voice, hopefully.
Yes.
Okay, good. So now I can be louder to speak to the in-person audience here. Just a moment. Okay, so then those improvements are.
Spare.
Okay, do you have spare? No.
I'll take care of it.
Oh, thank you so much. So those improvements are mainly because of the improved precursors emissions in this system, together with the constraints to the stratospheric ozone. Then for a longer term, the evaluation, we use the air-zomi decadal satellite ozone data. Then the improved agreement again demonstrate the good performance of the decadal ozone changes in our chemical reanalysis product, and also shows the great potential of this new ozone data, combining the airs and OMI, the spectral that we produced at NASA JPL. Then the analysis can also be used to infer the global surface ozone trend, which cannot be directly observed by any measurement. And we didn't use any surface measurement in data assimilation. But this reanalysis surface ozone is in good agreement with the observed trend overall for the United States and Europe. So that means the constraining the precursors emission were very essential to represent those ozone trends. Then in another study we conducted recently, we tested another multispectral ozone product that used the TESS and OMI measurement, so which were able to more directly infer the surface ozone data. So the satellite measurement have still the very limited sensitivity, the sensitivity to the near surface concentration, but they have the great potential for air quality applications, especially in conjunction with the chemical data assimilation system. Okay. Yeah. Thank you so much. Just a moment. My microphone is back. I need 5 seconds to set this. Okay, so I hope people can hear better now. Okay, then I don't have to loud anymore. Okay, then this is another example. The NASA's Chorus AQ. I see many people here who have been working or have worked on the Chorus AQ data analysis. This is such a great campaign that NASA and the Korean Institute conducted. And I was really glad to use the data to evaluate my chemical reanalysis capability using many the aircraft, the airborne measurement data they provided. Then we used this opportunity to evaluate the impact of the individual assimilated measurement on the improved representation of ozone over the Korean Peninsula. Then, as shown in this figure, we evaluated the relative importance of the individual measurement to improve the tropospheric ozone profiles over South Korea. Then, as shown in the green bar, optimizing the precursors emission was important to improve the lower tropospheric ozone. Then the assimilation of the MLS data, that's the stratospheric rim sounder measurement of the ozone and other species profile measurement, especially above the 215 hectopascal level, that provided the additional constraint in the upper level, the ozone, as shown in the purple. Then the exercise result demonstrate that importance of the simultaneous optimization or assimilation of the precursor and stratospheric measurement to improve the entire tropospheric ozone profile. Then we saw some changes in those relative contributions, depending on the weather situation. If that was stagnant or more like the long-range transport cases. But having that set of those measurements really helped to, for any cases, to have the improved representation of tropospheric ozone profile. Then we tested the assimilation of the new tropospheric ozone profile data. Then, it really helped to improve the ozone analysis for the quantitative attribution of the anthropogenic emission and natural influences. Then here now we see even more the opportunities in the near future. For example, this framework can be used to demonstrate the additional new contribution from the recent satellite measurements, such as the GEMS, and the Tempo and Sentinel-4 will be coming in the next few years. Then this framework will be useful to give the new scientific interpretation of the air pollutant over the entire broader Asian region during the Asia AQ aircraft campaign. So we look forward to that opportunities, and hopefully our system will be one of the good contribution to the science discussion. Okay, so the chemical reanalysis provides the important information on global air pollutants and its the attribution. However, still the systematic model errors must be quantified in order to assess their fidelity. We assume the perfect model in data assimilation. We assume model have the perfect representation of the chemical and physical processes. Of course, that's not the case. So we need to consider that effect on the data assimilation analysis. So we use the multimodal chemical data assimilation framework, the MOMOCHEM, to evaluate the impact of model errors on tropospheric chemistry analysis. So in this framework, we implemented the common data assimilation framework into 4 different chemical transport models and assimilated the multi-constituent satellite data. Then we integrated the multi-model analysis field to provide the integrated information that are less dependent on the performance of the individual model. And this can also provide the analysis uncertainty due to the model errors. Then for example, this system provided having the multiple model in the unified system provided the possible uncertainty ranges in the current top-down NOx emissions due to model errors by 13 to 31%. So the uncertainty information can be added to any emission and concentration field that the data assimilation system provides. So that can be propagated into the human health and climate impact assessment. I mean, how much uncertainty can be included in the emission data we use to assess their impact on the human health and climate would be very essential information to give the more meaningful discussion to the community. Then using this framework, we evaluated the surface ozone response to the NOx emission. So this plot is a bit complicated, but shows the seasonal changes in the ozone production efficiency estimated from the integrated multi-model analysis, so which is shown by the solid bold lines, and its uncertainty, which is shown by the shaded area for the tropics and the northern hemisphere. So the estimated ozone response is, in general, the larger in the tropics than in the northern hemisphere, so which implies the latitudinal shift in the NOx emission would increase global ozone because of the larger the ozone production efficiency in the tropics. Then it also shows that the ozone response changes by the factor of 2 among models, so which shows the fundamental differences in the first model processes. Then the observationally constrained, the multi-model integrated fields provide the fundamentally different first chemical processes than those in individual models. So that might be useful to get some insight into the model detailed chemical processes. So having multi-model capability is such a unique framework, I mean, to broaden the discussion we have had in the past. Then the two more recently, this is the recent analysis, to evaluate processes controlling ozone variations. During the wildfire events, we are working on some development and application of new satellite product. So as an example, the Chris atmospheric composition retrieval produced by JPL project that have been used to study the evolution of air pollutants during the wildfire event. In this case, those figures shows the 2020 California wildfire, the spatial map of AOD from BS, and the CO, ozone, and PAN from the Chris measurement. So then, as shown by the AOD measurement, the fire plumes, extended over the North Pacific. Then the CO and the PAN shows a similar spatial extent. And that's the same time that ozone shows a bit more complicated spatial patterns. So we use the model, the sensitivity calculations to understand the processes controlling the ozone structures during the 2020 fire events, with and without the fire emission and US anthropogenic emissions in this case. So the results shown here highlight the strong influence of the remote air on the ozone enhancement over the North Pacific and the North Atlantic Oceans, both in the lower and middle, the troposphere. And also this shows the substantial contribution from the wildfires over the Western United States, and also the over North Pacific Ocean in the lower, the troposphere. Then the US, the anthropogenic emissions have the very limited impact overall over the continent, not over the continent, but over the remote regions. Then we are currently working on several wildfire events analysis, including the 2019-20 Australian fires, using this framework and the new satellite data we are producing. Then especially assimilating those Chris data would comprehend the understanding of the more detailed processes that occurred during wildfire events, including the daily changes in the emissions that can be inferred from the assimilation of those new satellite data. Okay, then I'd like to change the topic a bit, but this is still based on the chemical reanalysis data. Yeah, we can infer the OH, the field, from the multi-constituent chemical data assimilation field. So there have been several approaches that used to constrain the global, regional, or local OH field. And because of the use of some multiple species that are related to the source and the sinks of the OH, we think that our OH fields are well constrained and would provide some insight into the OH variations. Then we validated our OH field. Although there's still large uncertainty, yes, should be large uncertainty in our OH estimate. Our analysis, compared against the atom observations, shows the much better agreement, than the model of simulation without any data simulation. So, for example, in the Boreal, the atom 1 is the winter season. The observed interhemispheric ratio of the OH concentration was nearly 2 near the surface, and it was nearly 7 in the free troposphere. Then in the opposite season, it was much lower, about 0.5 to 0.8 throughout the troposphere. And the model, without any data simulation, tends to overestimate that interhemispheric ratio. We know that's the really common problem in many models which have been shown in the ACMIP, CCMI, and the CMIP, the comparisons. Then the data simulation tends to reduce that ratio and gets much closer to the observed ratio. Then because the chemical lifetime of many species are affected by the amount of OH, so this improved representation suggests the importance of this data simulation to improve both the concentration and emission of many species, not only the air pollutants. And I can go this very quickly because I'm not very convinced by myself, but this can tell us the possible, the interannual and decadal changes in the OH for the entire globe, which shows the strong positive trend over Southeast Asia and the Central or Eastern Pacific, that throughout the troposphere, especially in the northern mid-latitude. So this would highlight the possible substantial impact of human activity on the entire tropospheric system, and also the lifetime of CH4 and other species, because of the changes in the emission sources of NOx, CO, and also humidity and lightning. So we have been conducting the more sensitivity calculations to break down the driving sources, separately. Okay, so it's almost 40 minutes. Then if I have time a bit.
Yeah, go ahead.
Okay, thank you. So I'd like to introduce the more recent study we conducted just after the pandemic. So we extended our analysis to the most recent years. So while many countries in the last few decades have implemented the environmental policies to reduce human health risk from air pollution, that impact have not been always clear. Then the global lockdown in response to COVID-19 represent the well-observed scenario of opportunities that allows us to assess how atmospheric emission and composition respond to reduced human activity. So this figure shows the time series, not yet. So this figure shows a time series of the anthropogenic emission of NOx from our top-down estimate in yellow, and the corresponding the CO2 emission changes from the bottom-up the analysis. So the global total NOx emission decreased by 8% in 2020, which is quite consistent, similar to the CO2 reduction estimated from the independent, the bottom-up approach. But those emission reduction had the detailed spatial and temporal patterns, as shown by this movie. So at the country scale, the evolution of CO2 emission reduction over time is strongly correlated with the the government response stringency index, which is shown in the upper figure, which is an indicator of the government response to the COVID-19. Then Chinese NOx emission rapidly declined from late January, corresponding to their first lockdown. Then in Italy, the early implementation of lockdown led to the earlier NOx emission reduction than other European countries. Then in the United States, the emissions started to decline from the early March, corresponding to the stay-at-home order at many states. Then this shows the time series of the monthly NOx emission anomalies due to COVID. So the global total anthropogenic emissions were reduced by up to 15% in May 2020. The regional total emission dropped by 18 to 25% for most of the developed country regions. Then the corresponding simulated ozone response using the NOx emission anomaly showed the substantial seasonal variations as a result of the changing the meteorological and chemical conditions, in addition to the changing the emission. Then the contribution of the emission from each region changes substantially with time. For example, the influence of the Asian emission increased after May and after April, so which became one of the most dominant contributor to the global ozone reduction. Then this map, or movie, shows how the tropospheric ozone reduction occurred worldwide. So in total, global tropospheric ozone burden decreased by the 6.5 teragram ozone, so which accounted for about 2% of the global tropospheric ozone burden. So while this may seem small, 2% seems small, but this drop is the 15 times more rapid than what has been viewed as achievable through even most aggressive emission reduction, the control considered by IPCC. Then the response of ozone extended from the surface to the upper troposphere, which provides important implication on the radiative balance or the climate impact of COVID due to the changing the human activity. Since the ozone reduction was observed from space, so we used the CRIS tropospheric ozone profile product. Then that showed up to 12 ppb reduction in the monthly mean ozone during this season. So there are many factors affecting the observed changes from 2019 to 2020 that can include some wildfire events and the meteorological anomaly. But the broadly consistent result between the observed and simulated ozone response suggests that the part of the COVID anomaly was observable from space in the free tropospheric ozone. Then the result is also quite consistent with the analysis of the ozone sonde measurement, which also showed similar reduction in the tropospheric ozone. Okay, so I don't want to spend too much time, but this shows just a few more, and I don't use too much time. Then this shows the ozone reduction corresponding to the emission decreases in each region separately, which shows the great contribution from the northern countries. But the emission reduction in the tropical countries also have substantial impact on the global ozone reduction due to the strong ozone production efficiency. So the where and when the lockdown occurred is important in determining the impact of atmospheric composition. Then among the many regions, we found Asian contribution was substantial. Just through the deep convection and the Asian monsoon circulation, that signal originated from the Asian emission reduction propagated into the broad region, into the globe. So which means the human activity in Asia can have very big impact on the global environment and also climate through radiative effect. So in this study, we considered the NOx emission reductions only. But we also considered, I mean, we don't know how much the reduction occurred for VOC, but using the model simulations, we obtained additional 22 and 26 reduction in global tropospheric ozone burden due to reduced VOC anthropogenic emissions. So the impact of human activity on the global ozone can even larger than what we found focusing on the NOx emission only in our study. Then, okay, I can finish. Then those ozone changes can also modify the OH amount a lot, with up to the 44% reduction in the tropospheric global mean OH concentration, which would increase the lifetime of CH4 by 4 months. Then from the independent measurement of the CH4, we've noticed the sudden jump increase in the atmospheric CH4 concentration. Then we use the box model considering that the 4% reduction in OH, and that we summarize that the part of the observed jump in the XGH4 can be attributable to the changes in the OH lifetime, lifetime of CH4 due to the reduced OH. So we are currently working on the estimation of the total climate of the COVID. That includes ozone, CH4, secondary aerosol, and CO2. So that would provide us some political, discussion idea on how to co-benefit climate and air quality. So that this was such a unique opportunity to test those response with many measurements that measures actual response in this complex system. So I can skip the final 2 slides, but just a few words. So that NOx emission information can be propagated into the fossil fuel CO2, considering some economic development. We can describe the AQ GHG emission trajectory as a function of GDP. So this is our new concept we just proposed, called the modified environmental Kuznets curve. Then we applied this scheme to make a prediction of FSCO2 using near real-time NOx emission data. So this is a new activity using the chemical reanalysis output. Then we are also working on the machine learning application. So the chemical data estimation can provide very comprehensive information on that system that could be used to make some better, spatial temporal interpolation and improving forecasting and the data quality assessment. So this is another new project we are working at another GPO. So this is a summary slide. So I don't have to repeat everything I already explained, but I see the future, the really exciting application opportunities coming in the next few years by utilizing the new satellite, the missions, the ideas and their data that includes the GOSAT GW, CO2M, GEMS, GeoCarbo, CO3, Tropomi Temp, GeoXO, and Sentinel-4. So we are trying to integrate those information in a meaningful way to give some new scientific insight. Then the AJQ will be another interesting campaigns, and we have some new focus on the trace gas aerosol interaction, OH, and there's many discussion going on wildfires, and also the Megan biogenic analysis will be another exciting application we might contribute to our work together in the future. Thank you. That's all I have.
Thank you very much. We have time for a couple of questions.
Just have a clarification. So you said that the NOx reduction resulted in a 6% reduction in the burden, something like that. But then you said VOCs was responsible for 25% reduction in the burden, and I was confused.
Okay, so the NOx emission led to 6.5 teragram ozone reduction.
Yeah.
Then I'm sorry, this unit is not correct. This is the tropospheric ozone burden in teragram ozone. Then the VOC 20% reduction led to the additional 22 to 26% reduction compared to the ozone reduction.
6 teragrams.
Yes,
So now it's 8 teragrams. or
Yeah.
something.
yeah,
Okay.
that's correct.
That's anthropogenic VOC only, or?
Yes,
Okay.
yeah.
Kazu, related to this slide, can you tell from this, anything about, NOx versus VOC control? And I mean, so it's all very complicated, right? You could not even getting the ozone reduction, but you're going to do it. But based on what was happening in different cities, can you see different things going on?
Yes.
In the ratios of VOC to NOx reduction?
Yeah, sure. So some cities that had the increased ozone corresponding to the reduced NOx, or combine the effect of NOx and VOC. It really depends on the city and the chemical regime, and as a total of the tropospheric pore air is always negative.
Yeah.
But if we focus on only the surface level at the urban city, that's very much complicated.
Right after the lockdown over, I think most of people take a look at the ground observation data. Like the report that I've seen was that most of the urban area ozone has been increased.
Yeah.
Due to mostly China, I think in the US too, maybe in Europe too.
Yeah,
Then global scale seems like ozone burden loading has been decreased.
yes.
And then we know that NOx lifetime is short, won't be able to get out of this urban scale.
Yeah, so that titration can occur
Right.
only in the central urban region. And we saw that consistent ozone increase in our model
Right.
simulation.
Then ozone hotspot, like urban areas, ozone has been decreased. An increase rather, observation indicate that. Then what is driving this increase of ozone burden or loading in the global troposphere? I just was wondering, like, how I can just connect the dots in them.
Okay, so I mean, for the global total, the changes in the remote areas were dominant.
Right.
And
Which is not really affected by the emission reduction of NOx due to lockdown.
yeah,
I guess there's no lockdown.
which was due to the NOx emission reduction over city. But because of the low level of NOx, the response
Right.
is so different over remote
There's a little
region,
bit of a change.
so
in
which
the,
dominates the global total.
Oh.
Yeah.
So here's my question. It's sort of a simple question. So if you had $100 million to spend on a new satellite,
Hmm.
going from space, or you could spend that money buying ozone monitors that were near the other 75% of the population on Earth, where would the money be better spent?
I'm not good at the financing.
let's say the unlimited resources.
I mean, I always try to escape from that discussion at NASA, how to budget. We know all the satellites are very expensive, and even some new satellite can be much cheaper than the current one, like the CubeSat. We could have a bunch of the small satellites to cover the entire globe. But still, we need some enhanced sensitivity to the surface. That to be able to contribute to the quality and human health assessment. So clearly, the ground in situ surface measurement is still needed for many developing countries. That's clear. So I'd like to put enough money for that. And I don't know how much it would cost. Then if we can cover maybe the 80% of the population, then we can start having some constellation of the CubeSat, or the two more geostationary satellites to cover Africa and South America, in addition to James Sentinel-4 and Temporal. But I know geostationary are so much expensive. So
I have a follow-up question to that. I think most of ozone data you showed us like 700 hectopascal. That's probably 2 kilometers.
yeah, 2 or 3, 2.5.
And then that's not necessarily the altitude people are living in. I guess, satellite data set has hard time to retrieve the very surface data.
Yeah.
Is there any progress in the front?
Yeah.
Or any-
So what we do is to use chemical reanalysis as a transfer function. So we can have the surface to that level ratio from the chemical analysis. And just applying the satellite information to that ratio will tell us the surface ozone data. That's one technique we already tested, and it worked really well. I mean, in the monthly scale, daily scale is really challenging. Then another approach we have been working is the multispectral retrieval. Even if the individual spectral retrieval has limited sensitivity, the combined satellite retrieval can provide much enhanced sensitivity to the lower atmosphere. So we're testing that capability with the many different set of the satellite, including the tropospheric combination and summarizes.
Any question from the Zoom?
I'm curious, I saw you submit a paper on that, but the impact for the secondary aerosols. So how much impact was that?
Okay, so that's still under investigation, but because of the substantial changes in the many aerosol precursors gases, including the NOx, ammonia, and the CO, that's not the aerosol precursor, but we saw the really big changes in AOD, and which was so in the agreement with the satellite observed AOD changes from previous years to 2020. So then we have also the primary aerosol reduction. I mean, that is directly emitted from transportation. That the separation has been really challenging because we don't have the specification and the aerosol component measurement across the globe. But we're using the model, we're trying to make that the relative contribution to the observed AOD changes. And based on that, we have the radiative forcing estimate. And it is much larger than ozone. Then the total climate impact can be much larger when we consider the secondary aerosol changes. I mean, given the precursor emission change information, we can make that two different estimate, I mean, for trace gas and the secondary aerosol. Then there's some more things happening, like the OH can change CH4, then the CH4 can affect ozone production. Then there can be short-lived effect and the more persistent effect of COVID through the information propagation. I mean, that originated from the precursors emission changes. But that information can be integrated in some part of the atmospheric system. So having the response calculation is challenging because time scale can be different depending on the processes or species we are focusing on. So how to summarize the impact analysis is a really new challenge, but that would be really useful for the future policy making discussion. I mean, for both air quality and climate. So what kind of impact can be obtained in very short term, and if that can be persistent for many years or not. So yeah, then the aerosol is the part of the discussion. Then I'm sorry, I don't have any numbers on the secondary aerosol impact, but I have some, I mean, how much PM 2.5 concentration changes were due to the COVID, the anthropogenic emission changes. So those are summarized in that paper. So I'm sorry, I don't remember.
Any other questions? Otherwise, we can hang out there, get some snack, coffee, and water. So that's thanks to the Kazu again.
Thank you.